Hi everyone, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book series I've been running for about 5 months on my three-volume series shown here. I'm doing volume 1. I'm on chapter 6 now, which is on group theory, and there's a lot of different kinds of groups I'm going to discuss. Today I'm going to start discussing a new one. But before we get into this type of group, which is called permutation groups, first I have to tell you what a permutation is. So anyway, let's begin. So permutations. What are permutations? Well, you're supposed to imagine, let's go back to set theory here. So we're supposed to imagine we have a finite set, which I'm calling capital S. I'm talking about finite groups here. That's why I'm letting capital S be a finite group. Besides, I think if S was infinite, we wouldn't call these permutations. We'd call them arrangements, I think. So we're only dealing with finite sets. And as an example, I give a set with 4 elements, just the elements A, B, C, and D. So what a permutation is, it's just a way of ordering these elements. So, the permutation is a function. That's the first thing you should realize. Remember, when I was talking about sets, I talked about functions on sets. This is what's called a bijection. It's a bijection from S to itself, also known as an automorphism. But anyway, it's just a function from S to itself. It maps every element of S to another element of S. And like I said, since it's a bijection, it's one-to-one and onto, which means that the range is equal to all of S, meaning every element of S gets mapped, and no element gets mapped more than once. It's one-to-one as well. So for the particular example I'm giving, I would say P of A is B, P of B is C, P of C is D, and P of D is A. That's an example of a permutation. It's what's known as a cyclic permutation. I think you can see that because A goes to B, goes to C, goes to D, goes to A, and so on. That's a pretty simple type of permutation, but they don't have to be cyclic. They can be more complicated. And there's a couple ways you can represent permutations. They both involve matrices. Actually, the first one, the first is a matrix representation. It's a 2 by n matrix where your set has a cardinality n. In this case, n is 4. So this would be I guess it's actually 2 by 4 matrix. So on the first row you write the elements of S in order, A, B, C, D, as you can see. And on the second row, you write what they get mapped to. So A gets mapped to B. That means B is right below A in this representation. And B gets mapped to C, which means C is below B. C gets mapped to D. D is below C. And D gets mapped to A, so A is below D. So that's how you do that. And in general, you would map S sub 1 to P of S sub 1, S sub 2 to P of S sub 2, and so on, all the way up for S sub n to P of S sub n, or your elements of capital S are little s sub 1, little s sub 2, all the way to little s sub n. That's a general way to do it. So that's the first type of representation of a permutation. Pretty simple one, and pretty easy to see what's going on with this kind of representation. But there's another very useful way of representing permutations, and this is known as the cyclic representation. So it turns out, I haven't talked about cycles yet, but I think in the last example we had a single cycle. I mean, you see A goes to B, goes to C, goes to D. We would write that cycle as, if you like, a vector. We would write it as all the elements at a single row with parentheses around it, A, B, C, D. That's how we would represent this cycle. But a permutation doesn't have to involve one cycle. As a matter of fact, it only involves one cycle, I think, if it's a cyclic. Yeah, if it's a cyclic permutation. But not all permutations are cyclic. And in general, you're going to get a product of cycles. You can just keep iterating this map P, this permutation map. Functions like a map. So you can start with I'm calling it S sub 0 here. So I guess S sub 0 is your first element of your set. and I'm saying that's S, and then S sub 1 is, that's just your first element. It can be an arbitrary element of your set capital S. So little s is, you're supposed to think of this just an arbitrary element of the set you started with. For instance, for the set I did in the last example, it could be the number 2. Could be not any of the numbers from 1 to 4. So we're just looking at S sub 0 and some fixed element of that set. S sub 1 is what it gets mapped to by this permutation P. So if I'd started with 2, it would get mapped to 3. Probably a little more natural to start with 1. So we start with 1, that gets mapped to 2, but then 2 gets mapped to 3, so S sub 2 would be 3. S sub 4 would be P of 3, which is 4. S sub 5 would now be 1 again. And once you get back to what you started, you close the cycle. So you would write this as 1, 2, 3, 4, like I said. But in general, you write it as S sub 0, S sub 1, S sub 2, up to S sub K minus 1, where K is the length of the cycle. So cycles can have any length. They can even have length 1. A cycle of length 1 is what's called a fixed point. The permutation doesn't do anything to that element. And we can have, remember, the identity element is an element of every group. I'm not talking about groups yet. It turns out the set of permutations of a set is a group, but we know that every group has an identity element. That means there has to be a permutation of every set that does nothing, that just leaves everything alone. That would be a product of one cycle. So a one cycle is actually a trivial group. It's a group that doesn't do anything. So you can have cycles of any length within a permutation of a set of cardinality n. You can have any length from 1 to n. And in general, you get a product of what are called disjoint cycles. That means that each cycle, there's no elements in common in any of the cycles. Yeah, I do this here. So this is an example of an arbitrary permutation. You can write, this is a general form of a cyclic representation of an arbitrary permutation of a finite set. It's just a product of disjoint cycles. So we would have S sub 0, S sub 1, up to S sub K minus 1. That would be your first cycle. And then I guess I start using different letters. You go T sub 0, T sub 1, up to T sub L minus 1, and so on. In general, you're going to get some finite number of cycles, and then you keep going until you've used up all the elements. Every element, the way you're supposed to think about what the permutation does is it kind of what's the way to say this? It breaks up the set into a product of disjoint cycles, and the cycles kind of show the action of the permutation on a given set of elements. So that's what a permutation does. It's kind of you can think of it as a product of a bunch of disjoint cycles of different lengths. So that's what permutations do. If it's a cyclic permutation, there's just one cycle. So that's how we would represent cycles. And I know this is a lot. This is probably a lot to take in. This is kind of new territory. So let's just do a couple more examples. So here's a more complicated permutation than the first one I did. So our set is the numbers 1 through 5. 1, 2, 3, 4, 5. That's our set S. Set of cardinality 5. And now I'm defining this permutation P. I'm saying P of 1 is 4, P of 2 is 2. I think you can see that 2 is a fixed point. P of 3 is 1, P of 4 is 5, and P of 5 is 3. Well, the matrix representation, or I'm calling it the permutation representation here, it's pretty easy. That's the easiest one to write down. I mean, you just write down 2 rows. The first row is your elements of your set, ordered in a nice way. And then the things below them are just the things that get mapped, that P, the permutation, maps those elements to. So like I said, 1 gets mapped to 4, 2 gets mapped to 2, 3 gets mapped to 1, 4 gets mapped to 5, and 5 gets mapped to 3. What about the cyclic representation? Well, to get the cyclic representation, we can start with 1. It's usually best to start with the first element of the set. That's what I'm calling S sub 0. So S sub 0 is 1. 1 gets mapped to 4. Now we see what 4 gets mapped to. and 4 gets mapped to 5, then we see what 5 gets mapped to. 5 gets mapped to 3, and then 3 gets mapped back to 1. So that's a cycle. That's a cycle of length 4. So that includes every element of X except the element 2, and 2 gets mapped to itself. So we can write this a couple different ways. We can write the cycle 1, 4, 5, 3. That's the cycle that included the element 1, every element except 2. And then you can also write 2 by itself in parentheses. But you don't have to write the fixed points if you don't want. I mean, sometimes we do that. Sometimes it's nice to do that, but we don't have to. So another way we could write this permutation is just the cycle 1, 4, 5, 3. There's only one non-trivial cycle, if you like. So that's how you would represent the P, this permutation, both in permutation representation and in cyclic representation. And let's do another example. The elements of your set, they don't have to be like numbers or letters, obviously. They can be whatever, sets can have arbitrary types of objects. Here, the objects of this set are the notes of the musical scale. Do, re, mi, fa, sol, la, ti. Might as well sing them. Do, re, mi, fa, sol, la, ti. I think you guys all know the musical scale. And here this permutation I'm defining maps do to mi. That would be do, mi, and then maps re to fa, and mi to so, mi, so, and la to ti, and then mi to do, or so to do, and then la, ti, and then finally fa, la. So that's what it does. Those are the that's what P does. Those are the way that each note gets mapped. And that's the permutation representation. What about the cyclic representation? Again, now you have to, do what we were doing before. See what map gets mapped to what. So do gets mapped to mi. That's do, mi. And then mi gets mapped to so, mi, so. And then so gets mapped back to do, so, do. And then re gets mapped to fa, re, fa. And then fa gets mapped to re, fa, re. So that's a cycle of order 2. That's called a transposition, by the way. Cycles of order 2 are called transpositions. And then we've got la and ti, and that's another transposition. La, ti, and then ti, la. So those are our cycles. So now we know we have do, mi, so. That's one cycle, and goes back to do again. And we have re, fa, and then it goes back to re, and la, ti, and it goes back to la. So that's a cyclic representation. And, you might recognize what I'm singing here. This is from The Sound of Music. I don't know if you remember the scene where they're doing Do, Re, Mi, the song Do, Re, Mi, and The Sound of Music. I must have seen this movie about 20 or 30 times. I love this movie. But remember when, what's her name? The nun in the movie, forget her name. The one played by Julie Andrews. Maria von Trapp. She's not Von Trapp yet, but she's trying to teach the Von Trapp children how to sing. So they do the song Do, Re, Mi, and there was a scene where they're sitting in a carriage and she's trying to get them all to sing in harmony, and they actually do this particular permutation of the notes. She has a little I guess, I don't know what you call it, like sort of like a wand, a pointer. She goes to each of the children and has them sing these notes in order. So these are the orders they did the notes, and makes a nice harmony. So I thought I'd give this as an example. So I guess there are practical applications of permutation theory applied to music. So maybe you'll learn something new. So anyway, that completes my video for tonight on permutations. Next time I'll talk about permutation groups. So thank you for watching. Long live math, and I'll see you guys next time. Bye.